Chapter 16, Humoral Immune Responses. The learning objectives for this topic are: contrast T-dependent and T-independent antigens in terms of size and repetition of subunits. Describe the inducement and action of a T-independent humoral response. Describe the formation and functions of plasma cells and memory B cells. Describe the steps and effect of clonal selection. Contrast primary and secondary immune responses. In this topic, we're going to go over inducement of T-independent humoral immunity, inducement of T-dependent humoral immunity with clonal selection, memory B cells, and the establishment of immunological memory. Some polysaccharides are really big and they have repeating subunits. They are big enough that they can cross-link several BCRs on a naive B cell. Because of the cross-linking, this stimulates the B cell to divide just a few times, relatively speaking, especially when we talk about T-dependent humoral immunity in the next slide, and they become plasma cells and start producing antibodies. Now, this is a relatively weak response, and it disappears quickly, and there's very little memory. So why would the body do it at all? Well, because these polysaccharide repeating subunits are from fairly common pathogens. One of the most common ones of T-independent humoral immunity is the capsule polysaccharides from Haemophilus influenza, which is a very common cause of pneumonia following influenza, and also it's a common cause of meningitis in young children. Usually doesn't cause meningitis in adults, and we think this is because children do not have their full range of B cells yet, so they're unlikely to get this T-independent humoral immunity. Therefore, they're not protected against H. influenzae. So we have a vaccine now. The vaccine helps prevent this from meningitis from happening in small children. Now let's move on to the more common inducement of T-dependent humoral immunity with clonal selection. So what usually happens is B cells are activated by interaction with T helper cells. Here are T helper cells. They're activated by antigen-presenting cells. See, in this diagram we have a CD4 receptor where the CD8 receptor is in cytotoxic T cells. And they become activated, and they start chatting with each other. Now, if this is a Th2 cell or a helper 2 cell, it goes looking for the B cell that matches its antigen. This antigen would differ from the T-independent antigens by not being a big polysaccharide with repeating subunits. So that leaves it open to just about anything. Although I do have to say that most antigens, remember, are proteins because they have complexity. They're usually big enough to have an epitope that's going to fit into that MHC2, and it's going to have complexity. In any case, the Th2 cell comes along, and if they shake hands, then it activates the B cell. Now the B cell starts dividing and makes a whole lot more of itself than if it's in T-independent activation. And we get some memory B cells because most of the clones of the activated B cell are going to become plasma cells. And plasma cells start pumping out antibodies. They start out with IgM, and then they will class switch to one of the others. Plasma cells, because they're pumping out so much antibody, wear themselves out. They only live about 1 to 4 days. So we've got to have memory cells to be able to replace them. Also, they need to be ready in case a Th2 cell comes along and says, okay, we got to go again, guys. And like with T memory cells, they're ready to go faster. Now let's talk about memory B cells and the establishment of immunological memory. Let's talk about the difference between a primary response, which is the first time you've experienced an antigen, versus a secondary response, and how we can tell the difference between them. Now, suppose we have given you a vaccine against tetanus. The tetanus vaccine is composed of a tetanus toxoid. There's a lag period. If we sample your blood, we're not going to find any antibodies against tetanus toxin until about day 3. Then we're going to start seeing IgM in your blood, in your serum. Long about here, we start seeing class switching, and we start seeing IgG. By the way, when we talk about seeing IgM and IgG in the serum of somebody that we've given a vaccine to, we call this seroconverting. If we were to expose you to the tetanus toxin, we're going to see production of antibodies much, much quicker, about in day 1 or less. And we're still going to see some IgM because those memory cells, they're going to start dividing and they're going to produce new cells that are still making IgM. But we're going to produce much more IgG. So you can see you have a better protective response from a secondary response than we do from a primary response. So we want to know this kind of thing when we're giving people vaccines. Also, there are some diseases where the prognosis is much better depending upon whether it's a primary response or a secondary response. Back in the day, I used to screen blood samples for the presence of antibody against Epstein-Barr virus. Epstein-Barr virus is the most common cause of mononucleosis, or mono, in the United States. Now, if I saw this kind of profile in college students, in other words, they're having their first exposure to Epstein-Barr in about their late teens, 20s, in that range, their prognosis was not as good as if I saw this kind of profile, where it indicated that it was a re-exposure or a reactivation of the Epstein-Barr. The reason for it being is, like with most childhood diseases, if you get them as a child, then it's not as severe as if you get it when you're an adult. And it's the same with mono. If you get it as a preteen, which most of us have, then it's more like a bad case of influenza or the cold, and you get better and it's less likely to activate and cause you mono later down the line. If you get it for the first time as a late teen or into your 20s, then you're going to have it more severely, and the virus is going to come out of latency more often. So the physicians wanted to know if this was a primary response or a secondary response. And we can tell that by looking at the antibody profiles. Well, that's it for this topic. Here's a reminder of what you need to learn from this topic.